Good morning. I am Devasena. In this lecture, we are going to discuss about feedback amplifiers. This topic is present in the subject Electronic Circuits 2. Feedback amplifiers and introduction. Harold Bloch, an electronics engineer, invented feedback amplifiers in the year 1928. Feedback is the process of taking a portion of an amplifier's output signal and feeding it back into the input. Feedback can be arranged to increase or decrease the input signal. When feedback is used to increase the input signal, it is called positive feedback. When the effect of the feedback reduces the input signal, it is called negative feedback. Process of feedback representation. Feedback, it is the process whereby a portion of the output is returned to the input to form a part of the system excitation. Let us see the representation. This diagram is a diagram of open loop amplifier. Here an input is supplied to the amplifier and an output is obtained. And this is the representation of a closed loop amplifier. Input is applied to a summer and from that it is applied to an amplifier. We are obtaining an output from the amplifier. A part of the output is taken from the amplifier and it is applied to the input through the summer. In this feedback path, we are having a feedback network. This forms a closed loop. And this is indicated in the diagram. Let us see the types of feedback. In positive feedback, the feedback signal adds to the input signal. For this reason, it is also called a regenerative feedback. Positive feedback is generally used in oscillators. If the signal feedback is of possible polarity or out of phase by 180 degree with respect to the input signal, then the feedback is called as degenerative feedback or negative feedback. Negative feedback is generally used in amplifiers. Positive feedback. When the feedback energy, that is the voltage or current, is in phase with the input signal and thus aids it, it is called positive feedback. The positive feedback representation is shown here. Here, the amplifier produces 180 degree phase shift. Similarly, feedback network produces 180 degree phase shift. So, the total phase shift from the circuit diagram is 360 degree. And this is indicated in the diagram. Here, the input signal as well as the feedback signal are in phase with each other. Therefore, it aids the output. Both amplifier and feedback network introduce a phase shift of 180 degree. The result is a 360 degree phase shift around the loop, causing the feedback voltage V suffix F to be in phase with the input signal V suffix in. The positive feedback increases the gain of the amplifier. However, it has the disadvantages of increased distortion and instability. One important use of positive feedback is in oscillators. Negative feedback. When the feedback energy, that is voltage or current, is out of phase with the input signal and thus opposes it, it is called negative feedback. This is represented in the diagram. In this diagram, the input signal is out of phase, that is 180 degree phase shift with the feedback signal. Here, this is indicated. The amplifier introduces a phase shift of 180 degree into the circuit. while the feedback network is so designed that it introduces no phase shift, that is 0 degree phase shift. The result is that the feedback voltage V suffix f is 180 degree out of phase with the input signal V suffix in. Negative feedback reduces the gain of the amplifier. However, the advantages of negative feedback are reduction in distortion, stability in gain, increased bandwidth, and improved input and output impedances. It is due to these advantages that negative feedback is frequently employed in amplifiers. Let us discuss about the comparison between negative feedback and positive feedback. Negative feedback. In negative feedback, the input signal and the feedback signal are out of phase by 180 degree. Positive feedback. In positive feedback, the input signal and the feedback are in phase, that is 0 degree or 360 degree. Negative feedback increases the stability of the amplifier. Positive feedback decreases the stability of the amplifier. Negative feedback reduces distortion. Positive feedback increases distortion. Negative feedback increases the bandwidth. Positive feedback decreases the bandwidth. Negative feedback is generally used in amplifiers. Positive feedback is generally used in oscillators. To see the classification of amplifiers. Based on the magnitudes of the input and output impedance of an amplifier relative to the source and load impedances respectively, amplifiers can be classified into 4 categories as voltage amplifier, current amplifier, transconductance amplifier, and transresistance amplifier. Let us discuss about voltage amplifier. A voltage amplifier is defined as an amplifier which provides an output voltage proportional to the input voltage, and the proportionality factor is independent of the magnitudes of the source resistance Rs and load resistance RL. This is the representation of the voltage amplifier, that is the Thevenin's equivalent circuit of a voltage amplifier. Thevenin equivalent circuit of voltage amplifier is represented here, where V suffix x is the source voltage, V suffix in is equal to amplifier input voltage, V0 is equal to amplifier output voltage, R suffix s is equal to source resistance, R suffix I is equal to amplifier input resistance, R suffix naught is equal to amplifier output resistance, and R suffix L is equal to external load resistance. If the external load resistance R suffix L is large compared with the output resistance R suffix O of the amplifier, that is, output resistance is very less when compared to the load resistance we have, then the output voltage is approximately equal to AV into VI, that is approximately equal to AV into Vs. Hence, the output voltage is proportional to the input voltage. A suffix V represents AV is equal to V0 by Vi, with RL is equal to infinity, and hence represents the open circuit voltage amplification or voltage gain. A current amplifier is defined as an amplifier which provides an output current proportional to the input current, and the proportionality factor is independent of the magnitudes of the source resistance R suffix S and load resistance R suffix L. Here is the representation of the Norton's equivalent circuit of a current amplifier. The representation of the current amplifier is here, where I suffix S is equal to the source current, I suffix in the amplifier input current, I suffix O the amplifier output current, R suffix S the source resistance, R suffix I amplifier input resistance, and R suffix O amplifier output resistance. The value of R suffix L is equal to the external load resistance. The amplifier input resistance Ri is smaller compared with the source resistance Rs. That is, Ri is very less when compared to Rs. Then the input current I is approximately equal to the source current. If the external load resistance RL is smaller compared with the output resistance R0 of the amplifier, that is RL is very less when compared to the R0, then I0 is approximately equal to AI into II, that is approximately equal to AI into IS. An ideal current amplifier has zero input resistance, that is Ri is equal to 0, and infinite output resistance, that is R0 is equal to infinity. AI represents AI is equal to I0 by II with RL is equal to 0, and hence represents the short circuit current amplification or current gain simply. Transconductance amplifier. A transconductance amplifier is defined as an amplifier which provides an output current proportional to the input voltage, and the proportionality factor is independent of the magnitudes of source resistance Rs with load resistance RL. Here is the representation of the transconductance amplifier. The transconductance amplifier is having Thevenin's equivalent circuit at its input side and Norton's equivalent circuit at its output side. This is represented in the diagram. If the amplifier input resistance Ri is larger compared to the source resistance Rs, that is Ri is very greater when compared to Rs, then the input voltage Vi is approximately equal to the source voltage Vs. The external load resistance RL is smaller compared with the output resistance R0 of the amplifier, that is R0 is very greater when compared to RL. Then I0 is approximately equal to GMVI. This is approximately equal to GMVS. Hence, the output current is proportional to the input voltage. An ideal transconductance amplifier must have infinite input resistance, that is Ri is infinity, and infinite output resistance, that is R0 is equal to infinity. The symbol GM represents output current with input voltage with RL is equal to 0, and hence represents the short circuit transfer conductance or transconductance gain. A trans resistance amplifier is defined as an amplifier which provides an output voltage proportional to the input current, and the proportionality factor is independent of the magnitudes of the source resistance Rs with load resistance RL. This is the representation of the trans resistance. In the trans resistance, in the input side we are having Norton's equivalent circuit, and at the output side we are having Thevenin's equivalent circuit. This is represented in this diagram. If the amplifier input resistance Ri is smaller compared with the source resistance Rs, that is Ri is very less when compared to the Rs, then the input current is approximately equal to the source current Is. The external load resistance RL is larger comparative with the output resistance R0 of the amplifier. Here R0 is very less when compared to RL. Then the output voltage V0 is approximately equal to RMII, that is approximately equal to RMIS. Hence, the output voltage is proportional to the input current. An ideal trans resistance amplifier must have zero input resistance, that is Ri is equal to 0, and zero output resistance, that is R0 is equal to 0. The symbol represents Rm is equal to V0 by Ii, with RL is equal to infinity, and hence represents the open circuit transfer resistance or trans resistance gain.